let's bring it back to the measurement problem. So how does this theory solve the measurement problem?
Well, what it does is it replaces this vague notion of observer with a specific physical interaction and object. You could say absorbers, but these are all just atoms again. So when we say emitters and absorbers, we really simply mean ordinary physical systems like a hydrogen atom. So for instance, take a hydrogen atom that's in an excited state. It's got a little extra energy in it. It means the electron is not in its lowest energy state. And these are actually a little bit unstable, these excited states. So this is our typical emitter. And then our typical absorber is say, an atom in a ground state. So when you have this situation where these atoms and the charged particles that are parts of the atoms, the electrons and so on, according to this direct action theory, this absorber theory, they are always connected by this time symmetric propagator. So they always kind of know, and that's what it really means for an object to have charge, is that it's constantly in a connection with these other charged objects. So they kind of have this connection allows them to have the potentiality for interacting in a higher level way in a transaction, which consists of the emitter generating this time symmetric field that propagates to various absorbers, potential absorbers. They respond, and it's merely more of a mutual process at the relativistic level. It's not like one happens before the other. It's a mutual interaction. So they're each generating a time symmetric field that has the kind of a phase relationship that results in this symmetry breaking where you get a collapse. So you get real collapse. This is technically called a non-unitary process. So when this happens, when you get this mutual interaction where they each generate their time symmetric field, and you get an effective offer wave and the conformations from the absorbers, this is the breaking of that linear Schrodinger evolution. So this breaks that evolution naturally by reference to a specific physical interaction. And you get collapse, you get real collapse, and you get a real outcome, which is a photon going from the emitter to one of these absorbers, the one that sort of won the actualized transaction. And that's all a measurement is. It's actually, measurements are always carried out through photon exchanges. And so the key here is you get real physical non-unitarity. And you get it not by tinkering with the Schrodinger equation, which, sometimes people think, oh, this is a spontaneous collapse interpretation. And that means it's not really quantum theory, and she had to tinker with it to, No, and nobody's tinkering with anything. We're simply saying if nature's behaving according to this direct action theory of fields, the fields themselves will do this, will break that unitary, that kind of unbroken evolution that seems to give you Schrodinger's cat will actually get broken at a very basic level between that, going back to Schrodinger's cat scenario, we'll actually you get a well-defined probability at any particular time that if someone were to open the box, that basically the Geiger counter would be triggered. And because there are so many, you can actually quantitatively show that the more emitters and absorbers that you have, the larger your system is, the more likely this kind of collapse is to occur, and this faster it will occur at a smaller microscopic level. So you don't get these macroscopic superpositions happening. You just, it naturally break down. So that's how it solves the measurement problem, by getting rid of this ill-defined notion of observer, because you can never define what you mean by observer, and saying, no, there's a physical interaction that happens among these systems.
I just want to clarify that last aspect about the macroscopic observer. So let's bring back the Schrodinger's cat thought experiment. I think I only understand tough ideas if cats are involved. So let's bring that setup back. There's the radioactive atom. There's the vial with poisonous gas. There's the cat. There's the observer. And there's the observer's friend, Wigner's friend. As you go from the radioactive atom to this macroscopic cat to the observer's friend, how many of these are quantum states? How many of these exist as a superposition? And then in this train of quantum states, how do you decide at what point to make the cut? What's in a quantum state and what's not?
Well, the cut happens naturally because based on how many degrees of freedom are involved in your setup. So in the case of an unstable atom and, take that unstable atom and a Geiger counter, the Geiger counter is already an overwhelmingly humongous collection of absorbers. And with that many absorbers, you can actually calculate. I have a paper for people who want the hardcore, nitty gritty. You can actually calculate what is the probability at any particular time that you're going to get a non-unitary interaction. And once you get to systems that, if you even get to like a human hair, then you're overwhelmingly likely to get a collapse kind of interaction, a transaction in a tiny amount of time. So the quantum state, you can describe anything you want by a quantum state. The point is, did you have a unitary process, a non-unitary process or not? And you can calculate the probability that you're going to have that. This is kind of a subtler level of we not only have the probability of a particular outcome, we actually also have the probability that you will have a transaction. It's a time-dependent probability, and you can calculate it specifically for any system that you have, but you have to take into account how many absorbers are involved, what are the states that those absorbers will be transitioning between, and so on. You have to put in all those details. And when you do that, for instance, you get, like, if you do that with buckyballs, which are these large carbon molecules, they're kind of mesoscopic. And if you run a two-slit experiment with buckyballs, which people have done, you can get some degree of interference, but you also get a lot of collapse happening because the interference is getting washed out. Why? Because these are large enough objects that the transactional process is about 50% likely to happen. You can actually calculate how likely is it that you're going to get collapse in that, and that predicts perfectly, the kinds of phenomena you see when you work with buckyballs. So that's basically it. Is that you get transactions happening. You can't know. You only have probabilities. You can't say for sure at what time a transaction will occur. And that is also according to the uncertainty principle that won't let you do that. But you can get a very well-defined probability such that, it's overwhelmingly, like, the chance that you could get a Geiger counter in a superposition, the chances physically that superposition would persist up to the point where someone opened the box would be like 0.00001, that it's so tiny, it's not zero, but it's so tiny that, you're never going to see it. So you get these well-defined quantitative probabilities for at what point in your experiment collapse is going to happen.